Welcome, everybody. It's my pleasure to introduce you all to the first instance of the Halmstad Colloquium this year. The Halmstad Colloquium is a distinguished speaker series organized by the two research centers at Halmstad University, Ceres and Kaiser, both of which are funded by the Swedish Knowledge Foundation, the KK Foundation. The theme for the colloquium is embedded and cyber physical systems. It's a real pleasure to have Professor Gul Agha with us today. Professor Gul Agha is a professor of computing at the University of Illinois at Urbana-Champaign. He is the director of the Open Systems Lab at the University of Illinois at Urbana-Champaign. His interests are in programming languages for open, distributed, and embedded systems. He has won several awards through his career, including the ONR Young Investigator Award. He's also a fellow of the IEEE. He has numerous significant publications, over 150 publications. He has supervised 20 PhD students. Many of us might know him well from the work on actors, which is one of the most cited works on actors. Has over 3,000 citations or so, or around 3,000 citations, I should say. It's a real pleasure to have you here, Gul, and we very much look forward to the presentation about actors today. Thank you.
So welcome. So I'm going to give sort of a basic lecture on actors, and then offline we can go into great depth. Of course, if you have questions, feel free to ask them either during the presentation or afterwards. So I'm going to focus on the actor model, and this is sort of an introductory talk as I was asked to give. And so let's talk about actors. The world of actors has been growing. I started working on it almost a little over 30 years ago. And it's seen a resurgence in the recent past 5 years. It's finally sort of gone mainstream. So you have languages, Erlang being probably the most common, but there's other languages like E, and Microsoft had experimental languages like Axum, and of course versions of Python, and a growing list. There's a whole bunch of frameworks. So they're programming languages that are translated with compilers, and then there are frameworks that have been written that are basically been written in Java, but it's sort of a scaffolding that you can remove, including Scala, which is probably the best known, and a couple of them that we worked on, Active Foundry and Salsa, Kilim out of Cambridge, and so on. But the list keeps growing. In fact, recently, Google, or last year I should say, Google announced an actor language called Dart that they are promoting. Actors have been used directly for many decades. I mean, the Martian rover, for example, used the actor model to guide it back in the 90s, and it's quite a natural model given the delays between the Earth and Mars in communicating with the rover. The molecular dynamics code is probably the best known. It's basically an actor framework written in called Champ++ by Sanjay Kale at Illinois. And it accounts for almost 10% of the cycles at the National Center for Supercomputing at Illinois. And then there's a bunch of more familiar things like Twitter's message queuing, the Lift Web framework, image processing in the Visual Studio, 2010. It's done with a library they call asynchronous agents, which is an ACT library. Facebook chat system, this game engine involving 1 million users. So anyway, so I'm going to sort of define the basic ideas and then also discuss these different frameworks and some of the differences you see and what motivates them and how research needs to address some of the challenges. So that's the basic flow. So the first thing that I will do is to define the model. It shows up in variants. So these were sort of more pure programming frameworks, but it shows up in variants for real-time computing and event-driven computing. The Ptolemy framework, for example, from Berkeley, uses the actor model. You see versions of it in different places, from operating systems to real-time systems. So let's define the fundamentals of the model. The actor model involves concurrent actors or concurrent objects, which are actors. They're autonomous and they are inherently concurrent. So in a way, the model is very intuitive. We think of agents in the world, for example. That's the programming model for agents would be naturally actors. If you think of the model of object orientation, the idea of an encapsulated object, well, if you add concurrency to the object, then basically that's what you get is the actor model. Now, of course, people think in terms of concurrent objects. They think Java, for example, with concurrent objects. However, in Java, the model of concurrency is separate from the model of the objects. So you have threads for concurrency. The two are not unified. But in case of actors, we unify these two things that I'll explain in a moment. So a key idea is not to have any shared state. So a major issue in Java, for example, is these data races to shared variables. And they're caused because of this kind of sharing structure. The story I'd like to tell is back when I was starting computer science, my first courses, although I didn't major in computer science as an undergraduate. But my first courses, you sort of read about things like avoiding global variables. Don't use global variables. Why not to use global variables? Well, because it's very hard to figure out when things are shared, who's making the change. And then, of course, we got objects, and the key idea in the objects was, again, to avoid sending things around in a way that sort of shared them. Somebody else clobbers the variable. So somebody should own this thing. So now we come to the world of concurrency. Instead of a single thread of control, and all of a sudden we see these shared variables back. And we couldn't figure out these shared variables in the world of sequential programming. With a much more complicated world, naturally, basically it's been a bonanza for researchers to figure out data races and so on. So we'll come back to this issue of data races I'll mention, but unnecessary data races are created. It just complicates the program with this notion of sharing. Also, fundamentally then, it's a model of message passing. So if you have things that are isolated, and if you take a basic notion in physics, although in physics it's no longer true because of quantum mechanical entanglement, but the idea that there is no action at a distance. It's a very intuitive notion, so therefore to affect something else you have to communicate. So once you've eliminated any idea of sharing, you have these autonomous actors. To communicate, they have to send a message. And the message has to travel through space, and so the natural model of messaging is asynchronous. So the primitive model of messaging then is asynchronous, and this provides both for exchange of information or sending information and for synchronization. So the standard actor semantics then is encapsulation, which is the state encapsulation or isolation of the state. A notion of fairness, so when you send a message, it's eventually received. So this notion of fairness makes it possible to reason about eventuality properties. So in sequential program, for example, you have two kinds of notions. You have the notion of partial correctness, which says that the program never gets into a bad state, and total correctness, which says that it terminates. So partial correctness says, well, if there is a result, it's a good result, and total correctness says there is a result. Now, what total correctness requires is, for example, an assumption that you have an infinite stack. If you write a recursive program, then you take its fixed point, you say eventually the factorial is produced. In reality, of course, you only have bounded stacks. So programming is a process of abstraction, and the question is how to find the right abstractions to represent what you want to represent. And of course, if you were concerned in a practical sense, you would then reason not only about the program, but its implementation and what resources are available, what the bounded stack limit might be, whether you would actually succeed in getting it. And most of the time, programmers wouldn't have to worry about the height of the stack. Similarly, fairness is a notion that says if you send a message, eventually it's received. So what this does is to allow you to reason not only about safety properties. In concurrency, we talk about safety, which is like partial correctness, which says program doesn't get into a bad state, and eventuality properties, which are the liveness, so-called liveness properties, that something happens eventually. Right? So fairness allows you to reason. So you send a message, it's eventually received, some computation is eventually done, the actor is eventually scheduled, and so on. So that's a basic notion of the model. And then location transparency, this gets a little more controversial, but the idea is just like we don't worry about memory locations in a sequential program where the program is executing in memory, and of course it gets relocated all the time. Similarly, in the concurrent world, if we write a program, perhaps we shouldn't have to worry about where it's being executed. So whether it's being done on this core or that processor or wherever it's being executed. Now again, of course, in a practical context, you might have optimizations in the system underneath. It might worry about it, or you might have some separation of concerns, allow the programmer in a certain context to say something about the implementation. But in the pure model, you basically want to avoid talking about location. So this then also facilitates mobility, so things can move around and the underlying system can take care of where things are. All right, so I already mentioned basically the notion of isolation and sending messages. So there is no shared state. What this means is that when you send a message, it amounts to sending by value. So you don't share the contents of the message after you've sent them. So now, of course, in a practical implementation, you might relax this if you send it and you're not going to then change it or even access it, this value, then, or if it's a constant, for example, then you might actually in the implementation have sharing. So the abstraction should not be confused with the implementation, because the implementation will have optimizations and also practical limitations. So, of course, what this encapsulation does is to simplify the reasoning. Basically, instead of having to worry about interactions to variables that may change underneath you, you can think of this actor and it makes changes to its state, so its state is always consistent when it processes the next message. Or at least you can localize your reasoning and say what's happening within this actor, and I don't have to worry about what anybody else does while I figure out what I'm doing with this message. So you can essentially serialize the messages and not have interleavings of the messages. So now this, in fact, things like Scala and Kilim, they are active frameworks, but they don't enforce this. So these are conventions which say, okay, what you should do is send by value, and you should not create sharing. But they don't actually enforce it as a framework. And I'm going to talk about why they do this and what the issues are and how we might get around it. Another thing that I talked about in the pure actor model was this notion of fairness. So let me define, there are various ways of defining fairness. I'll give you one definition that's commonly used for actor semantics. I need a couple of notions. One is a notion of a permanently disabled actor. So a permanently disabled actor is an actor which is sort of executing an infinite loop, or it's blocked on a call because it's the wrong parameters, or some way it is stuck, essentially. It's in some kind of an internal deadlock, if you will, although the term deadlock may not be the best term to use in this context. An enabled actor is an actor which is not permanently disabled and has a message pending, so it has something to do. So actors are message driven, and if there's a message pending and it's sitting idle, then it's not permanently disabled. So the notion of scheduling fairness says that every actor that's enabled is eventually scheduled. And the notion of message fairness says that if you send a message and the actor that's receiving it is not permanently disabled, then eventually that message will be received. So these are the notions of fairness. So now, of course, this kind of just active fairness means that you cannot have a non-cooperating actor occupy the thread indefinitely. So if an actor is an infinite loop, which need not be an error, for example, it might be sort of perfectly legitimate infinite loop. It keeps sending, for example, I'm here message or something, or it's a clock that keeps sending its value. So it should be an infinite loop, so that in a concurrent program, interactive program, infinite loops are not necessarily bugs. They would, though, become a bug if you didn't have fairness at the level of the actors, because they could then potentially starve other actors. Because we're location independent, this means actors may be shared on a single node. They may be sharing the same processes or the same physical threads, machine threads, or they may be distributed. And of course, this means that if there's an actor in an infinite loop that doesn't yield and you haven't done the right scheduling strategy, then you would not have fairness. So fairness is something that's critical in libraries, and you can also see this in interaction with sort of plugins. You get a plugin that goes into a loop and your browser is dead. And that's because they haven't gotten the actor semantics quite right, because it should be having fairness between different things. And then, of course, you'd have degradation with a plugin that's every time it gets scheduled, it eats up some resources, but it wouldn't kill the other actors. Location transparency helps with things like load balancing, because the system can move resources around and things of that sort. Now, just to take the frameworks that have been defined in terms of Java, in fact, all these frameworks have been implemented in Java, they in fact ignore, so they've got the basic actor concepts of keeping things actor-like, and that's what they are also, if you look at what they're recommending on how they should be used, it's an actor semantics, but they actually don't enforce things like this encapsulation of the state, or even safe messaging in several of them, fair scheduling. Some of them have it, some of them don't. And so there is kind of a interesting question on why these systems are actually not providing all these things. And there's a reason for that. And of course, the most successful ones haven't provided all these nice features of the model. Although they recognize them, if you read the manuals and examples and so on, they'll say this is what's a good practice, or this is how you should use it. Although occasionally they actually contradict each other. Now, the Active Foundry is a framework that we've developed at Illinois, as we have, in fact, these three. So we have sort of been religiously fanatic about keeping these features. So we look at this thing, and let's dive into the anatomy of an actor and what the runtime system looks like, what it means to sort of define an actor, and then come back and see why they might have actually compromised on these things. And that will lead us also to some interesting research issues. So now, if you think of an actor and you need to implement an actor, then conceptually it has a thread of control. It has a state and some methods, and then this message asynchrony of messages going in and out of the system. So essentially, the encapsulated state and behavior, which is the methods, is what you think of when you think of objects. And so that's a notion of an object, and what we've added to that object is the notion of this independent control, this thread of control. And then, of course, these messages are coming in, and so different senders may send a message at the same time, and the actor may be busy when the message arrives. And now this idea of guarantee of delivery means you don't just throw away the message when it arrives. So they get executed in some order, which will be the source of the non-determinism in the computation. And so you need some kind of a mailbox or a mail queue where these messages are buffered and then processed some fairly. So now some systems, in particular, like the Scala, they have explicit control and a mailbox. And so basically they've given you this, this kind of Java library which defines it in a loop, and messages are put in a mailbox. There are others which have just defined a framework which provides explicit control. They go in a loop and pull messages, but now the problem of even coming up with the structure of the mail queue is left to the programmer. So this is essentially what the frameworks are doing. In case of the active Foundry, you have location-independent addresses. So you get away from Java addresses. This provides location transparency. You basically have to then manage your own namespace. You have asynchronous messages, and control is also implicit. The names are transparent to the location, and the mail queues and so on are separated out. You provide this. Essentially, there's an implicit loop which is taking messages. Programmer doesn't write a loop. What they write for methods basically means the message handlers in this context. So you don't explicitly deal with this loop where you're pulling messages to process them. So that's what the Foundry does, and of course then one of the goals always is reasonable performance. If you're theoretically minded, you set up this library, students can play with it, and that's great, and they go away, but then they say, oh, what about efficiency? So you've got this structure, you've got the encapsulation, name, mailbox, message comes in, you dequeue the message, process it, take another message. When you're done, process it, and so on. And basically then you've got very simple implementation. You've got actors which are like Java objects. They have an implicit receive, and you can give each of them a thread of control. Then you have lots of these green threads which are allegedly lightweight. But of course, there'll be sort of efficiency issues that arise with that. So this idea of a Java object plus Java thread plus a mailbox plus the actor name is a relatively heavy-duty idea. So in the languages that, for example, we built, if you have fine-grained actors, this would be a huge amount of overhead. And so what you would do, in fact, is if the actor is local, you would, in fact, never create. You would turn it into a function call. Now, of course, you have to deal with the issues of fairness and so on, but you have enough control in a compiler to be able to do that. In this framework implemented naively, you get all this overhead. Now, of course, if each actor is doing a lot of computation, for example, in the Charm++ world, where they have a C++ framework, each actor is doing a whole bunch of computation. Then this overhead is nothing to worry about because you have this huge amount of computation. But if you take something like a factorial and turn every recursive call into a message, you can get huge amounts of slowdown. So we've thrown in sequential computation by having a sequential language as the base as opposed to a functional language, but now you have sort of this variable grain size. So anyway, so there's a structure of the Foundry. You have name services and transport layers and request handlers and a scheduler and something managing these actors, and this all infrastructure allows you to write programs very abstractly, and that's the benefit. The things you'd have to do by yourself in terms of dealing with protocols become abstracted. So if you were to define actor language, as I've shown you, there are dozens, literally probably hundreds by now. They used to be in PhD thesis, but now even in industry they're defining all these frameworks. One reason is because it's very easy to do. You can take your favorite sequential language, and now you've got multi-core programming or something. You add the notion of creation. You add the notion of sending messages. And if you're dealing with a functional language, you have to add the notion of become to capture state change. Now, in the sequential world, your computations are all functions. The denotation of a computation is a function. So side effects are simply an optimization. If you change the state, it's just an optimization. You're really looking from an input to an output. In the world of concurrency, this is no longer true. So I don't have time to go into the mathematics of it, but essentially in the world of concurrency, when you have an open system, you have interactions. So for example, if I have a bank account, the bank account can have deposits and withdrawals. If I send a withdrawal message and my spouse sends a withdrawal message and we both want to withdraw $200 and there is $250 in the account, one of our withdrawals will bounce. And the only way you can represent this is by the state of the bank account changing, because otherwise every time the balance changes you have to know who might access it, update their state, and they then have to use the new state, if you will. You can take any sequential program and turn it into a purely functional program by doing CPS transforms. You basically send the state as argument to the continuation, and you have a sequential program that's totally functional, even if it was imperative. So anyway, so this sort of a technical aside, so you need a concept of become if you're in a functional language, which says that after you process this message, what is the function that responds to the next message? Now typically, and I'll come back to this, the languages also have request-reply messaging. So here I need some information, I ask for a withdrawal. Based on the response I get, I'm going to then take the next action. And so I cannot proceed until I get the withdrawal. Or the account gets a withdrawal message and there isn't enough money in it, and it wants to send a message to see if an overdraft is going to be approved to a different actor. So then it cannot respond to this request for a withdrawal until it has an answer from something else. And this kind of situation arises. In procedure calls, of course, everything is sequential. In the world of concurrency, you have to then explicitly either manage it in terms of sends and receives, but it arises often enough that you often have this request-reply semantics, which we'll talk about in synchronization constraints. Okay, so we've got a lot of benefits from this Foundry, extensibility, usability, and so on. Let's talk about efficiency. All these things are compromised. So we take an extremely stressful case, if you will, for thread ring. So as I said, if you have a lot of computation, the overhead gets amortized and there isn't a big difference. But how about if there's no computation, you just send this message around 10 to the 7 times in a ring, not even that many messages happening, so there's not any parallelism even in this, there's just one message going down. And if you look at, well, what happens, so Haskell threads, not really anything happening there. You take 6.7 seconds. If you take Erlang, reasonably optimized, 7.49. So, you know, you get these systems that are optimized, and then pure sort of Java things, which haven't done much, which allow references, passing by reference, and so on. And you take Active Foundry, this nice framework, and it takes 13 minutes. So we try to figure out, okay, what's going on and what can we do about this? And you can sort of see the chart there with all these frameworks. And Killim is a library which uses a weaver, and so we say, okay, well, one of the things is that if you map every actor to a thread, that's expensive. How about mapping a bunch of actors to the same thread? Right? And so this Killim did this through a bytecode transformation. So let's try that. And when we try that, you have this M to N architecture. M actors are mapped to N threads, and so you can have a bunch of actors hanging off a thread, and you don't create too many threads. The performance improves by 50%, or goes from 13 minutes to 7 minutes roughly. And so this idea of sort of worker threads, and then they pull actors, and you've got the runtime scheduler doing the mapping, and you can imagine. So it turns out, so that's 7 minutes, but that's still a far cry from the other systems. Turns out the major cost is the serializing and deserializing objects for sending them by value in Java. So here you can say, all right, what if we got rid of copying if we send all the messages by reference, which of course in principle could destroy the semantics, and which is what all of these frameworks have in fact done. They've allowed programmers to send it by reference and then told programmers, by the way, when you do that, you're breaking the actor semantics, so write your program so that it doesn't violate the semantics. And you can see why. So that's the difference. Now you're down to, here this thing was taking a factor of 20 right there in just serializing, deserializing. So if you just take the thing and add a send by reference and call by reference, the call is this RPC-like messages, comes down to 30 seconds. Now you're in the same ballpark. Why do we have an overhead? Well, because we have fairness. These guys don't have fairness. You have location independence. These guys don't do that. Location independence means that you're going to have to figure out who to call, whether it's local or remote, and so on. So there's a bunch of reasons. And that's why you see these zero copy messages and leaving it to the programmer. So what we did here, which I won't get into details, now I think things start working, which is good, and people start using them because it's efficient, but semantics is where bugs get introduced and so on. So we went back and said, all right, this is not nice, what do we need to do here? So we said, well, how about if we look at the program, analyze the program, and figure out, is this thing get used? So your semantics is call by value, and if most of the time you send this over, you're not going to touch it again, which is of course the case, for example, if it's a scalar value, constant value numbers, but very often this may be the case, then we will just send it by reference. So the idea would be to use static analysis then and figure out, is this needed? And there might be other iterations. I mean, they're sort of open for research. You might do this lazily. You might, because static analysis will miss a lot of cases. So essentially what you want to do is change the send to a send by reference when there is no conflict, right? With the fairness, again, you can take this Killim thing and modify. And now, Killim didn't have fairness, but if you allow a new worker thread to be launched, so if you have n threads that have been blocked, or on m threads, n actors, and now these m threads are blocked, then you launch a new thread, then you can maintain fairness. So you have some degree of fairness because it's, one thing is not starving everybody, but if m things are cooperating and starving and they're on different threads, you still lose fairness. So you can keep the correctness but be conservative. So that's the basic idea. And when you do that, you get performance that's comparable, and sort of ignore this. And of course, you've got dynamic load balancing and things of that sort. Naturally, this doesn't get over the problem of speedups. They're still constrained by the parallelism in your algorithm. So if you have an inherently parallel algorithm, you're going to have more potential for speedups. If you take something like quicksort, you don't have much potential for speedup, because as long as or the naive sequential quicksort, as long as there is a step that takes linear time, namely figuring out the lessers and greaters from the pivot, then your speedup is going to be log n at best, because all you can parallelize is after you divided the array. So your algorithm has to have a degree of parallelism, and that gets into more complicated issues, but it's bounded by the number of actors and how many messages they can process at the same time. And then, of course, you've got high-level constructs and so on, and we can talk about the high-level constructs. So, by the way, the static analysis that I mentioned that we did, I showed you just the chart very quickly. About 80 to 85% of the time, programmers are identifiably, from static analysis, we could tell, using only sending by reference was safe. So even though they are sending them, they're not reusing that variable. So if it's on the same node, you could just do it by reference. So that's why the results were looking good. All right, so I mentioned now programming abstractions. So now you've sort of got some simplicity, but it's not the end of the story. You want programming abstractions that are friendlier, and sometimes there are trade-offs, and you're going to lose something and gain something. So one of this was this sort of notion of callbacks. You send a request, you get some callback, and then you proceed. And of course, the sequential world, this thing is only one thing is active at a time. Here you have a bunch of things that could be parallel. And of course, this callback mechanisms introduce problems with how the state is to be dealt with. One idea of futures tries to deal with this by the idea that you send a request and get back a handle, you proceed with that handle, and then if you need the handle, then you're going to busy wait. So this is something that's been used in functional languages, for example. You could have synchronous callbacks where this thing is blocked, you send a request and you get a response back, and then of course you have poor cache performance and so on. In the actor world, typically it's broken up, these kinds of calls are broken up into a continuation passing style, a concurrent continuation passing style. So you send a message, and then you have a continuation method that's going to deal with the answer. If you have a state dependence, if you don't have a state dependence, you simply transform this code to create an independent actor which is going to proceed to do the rest of the computation. So by doing this, you can keep it message driven. And now there is a notion of sort of local synchronization constraints that I'll talk about in a minute. So in this example I gave you, you send a message and now you're waiting for the answer. Let's suppose there's state dependence. And then you're going to continue with that answer. So the problem becomes, of course, you might get other messages while you're waiting for this answer. And what you have to do is to defer those messages. This kind of situation arises all the time. So if I have a spooler and a printer, the printer says, I'm free. Do you have a job? Now it makes a request for the job, but the spooler may be empty. And there's no way to know that the spooler is not empty. You might say, well, let's query the spooler. So say, can you take a job now, for example? And the spooler says, yes, I can take a job. And then, it gets 5 other jobs, and you send a job and can no longer take it. It has to defer it. So you have this situation where, because of the asynchrony, unlike the sequential world where you could just do a test and check, is the buffer full? No. Unqueue. Here, if the buffer is distributed, you say buffer full? No. Well, by the time you unqueue, it may not be there. So you need sort of synchronization constraints, and they're dealt with differently. And this is kind of a very simple example of coordination. It's called local synchronization constraints. So it changes the order in which messages are being processed. One simple way to understand this is in the object-oriented world, we separated what was done from how things were done, the interface from the representation. However, when things were done was completely constrained by the program. When you make the call, that's when things get done. In the world of concurrency, when things are done is much more fluid. But that doesn't mean every order is a desirable order. So you need to sort of constrain these orders in some logical way. And this was a simple example of sort of a two-party interaction where the order needs to be constrained. And you can, of course, generalize this to multi-party interactions where the order needs to be constrained, because it's under-constrained if you just let it asynchronously operate. So actor languages typically then have some notion of these local synchronization constraints, and they do different things, and they show up in different ways. For example, pattern matching in Erlang and Scala, in disabling constraints in the Foundry, and they have different semantics. So what do you do with a message that arrives? And for example, the semantics in the active Foundry just defers it. Some other languages essentially say, no, you should say you're going to reject it. So for example, in the language Axum, essentially to communicate between two actors, you need a protocol in the middle. So you have to agree with this actor. So A and B will agree with the protocol. So they say, I want to communicate, here's the protocol. B says, yes, good. And now A must follow that protocol. And B must guarantee that it will respond if that protocol is followed. So the moment you say, are you full? It will no longer allow itself to get empty. If you say open and then a file, if you've got a file and you say open, then it's going to be open as long, and the next thing you can send is read and write. But if you send a read and write before, then it will simply reject that. So by having these protocols, you could then essentially define state machines. They define state machines which follow this protocol. You establish, for example, a sync plus ACK protocol, and then that will be the nature of the communication. I won't go into details of this contract since our time is limited. But of course, one thing I want to point out is take some protocol like a sliding window with some number of messages that could go through, and you get a rather complex finite state machine. So the way that Axum's approached expressing these protocols is rather complicated. You can, in fact, what we've done instead of these finite state machines is to use constraints, which are much more painful to implement. And of course, if you can translate this constraint into a finite state automaton, that's good, but in general, they will be much more complicated to implement. However, they're much friendlier to the programmer. And since that's our philosophy, so in this case, the sliding window protocol, there it was just size 3, and for size 4, I mean, just sort of exponentially blows up. You can just express it as a constraint where size is a parameter, and instead of all these automata that basically are subject to a lot of bugs, you can have a simple thing which says, okay, disable when the last frame minus the last ACK is greater than or equal to the size. And that's a simple constraint that changes the order of execution of messages. This, as I mentioned, can be generalized to multi-party interactions, and one of my students wrote a nice thesis on this subject, which was published by MIT Press. You can look at this notion of synchronizers, changing the ordering between actors. So anyway, so this large-scale thinking, you have to start thinking of loose synchrony, and then you have this problem of coordination between these different things. So let's talk about now what kind of issues show up, a little bit about reasoning in the last 5 or so minutes that I have left. So as I mentioned, one of the wins that we had was this idea that there aren't interleavings. In response to a message, you do some bunch of stuff. And nobody interferes with this bunch of stuff. Right? And so this basically allows you to have a macrostep semantics. So what this macrostep semantics says is you don't need to consider all possible interleavings. So if you think of sort of 2 threads with some shared variable, you have to think every time the thread does something, does it affect this variable? And so you have to sort of consider all these interleavings. If you've got m steps over here, n steps over here, then you have sort of, interleavings of m plus n steps, choose m, huge number, right? And if you just have these m steps atomically, then you just have sort of 2 possibilities of the interleaving. So that's the basic idea. So it raises the granularity of abstraction, and also because your messages are asynchronous, you cannot have deadlocks. So if you have synchronous messages, a very trivial example of deadlock, if you had a process with synchronous message, it calls itself, it's going to deadlock. So, but if you have asynchronous messages, then you're not going to cause deadlocks. But, yes?
Maybe you answered that, but does introducing synchronizer not bring the problem back?
Well, yes. So in fact, even before the synchronizer, this RPC-like communication, so you're not deadlocked, you're live, you're willing to accept a message, but if the response never comes back, you're not going to do anything useful. So you can still have sort of these live locks. And so in your coding, for example, you might have an error handler saying, hey, what's going on? And then you're disabled for processing that message, other messages, except messages that have to do with debugging, for example. So you have more possibilities. So the problem doesn't go away. Even the inconsistent state updates, problem went away within the actor. And so you could write logical coherent pieces of code that were functions or things that had to be done together. But you could still have inconsistent state between actors. So if 2 actors need to make a change for whatever reason, like a fault tolerance protocol or something, then of course you have again issues of consistency, right, between independent agents. So these problems don't go away, they just are raised to a different level of abstraction. They are still there, and so techniques, of course, have to be developed, and of course there might be old-fashioned bugs. So we need methods for reasoning about these programs. Now, what I'm going to do is just give one example of a kind of technique for testing what happens in concurrency, what the difficulty is, and what are some ways of addressing it in the next maybe 2 minutes. So what we can do is test a lot of states, and of course there are other techniques like model checking and so on that I won't go into, but you still have this possibility of exponentially many schedules. So even though they're not exponentially many schedules in terms of different actors being interleaved at the fine-grained level, you still have many actors. So if you've got hundreds of actors or something, then you have a very large number of potential schedules. So what you have to do is to figure out what parts of these schedules are, some student of mine had enough time to make these animations, what parts of these schedules are essential and what do you need to actually test. So here's an example. There's a bank, and banks somehow make nice canonical examples, and she deposits $1,000-something or whatever, Swedish krona maybe, and sends a message saying, hey, I finished depositing this money, right? And then he sends a withdrawal message for this 1,000. And now you can guess what might happen, right? The finished deposit may come first, and the withdrawal message may go, and things may actually bounce. So, so you've got this state. Initially, you've got this deposit and finished deposit message, so there are two possible transitions. Could be the finished deposit transition or the deposit transition. If the deposit happens and then the finished deposit, and then the withdrawal, you get this execution. And let's see, if the finished deposit happens and then the deposit message arrives and then the withdrawal, you're still okay. But if the finished deposit happens and then the withdrawal, then you have a problem, right? So this thing would lead you to a problem. But the interesting observation is that in this case, the order doesn't matter, right? So what we do when we are testing the programs is if we have seen this before, what we want to do is to avoid executing this path, because it's not going to give you any violation if this hasn't given you a violation. So this is a basic notion of partial order reduction. Of course, the Macrostep semantics is also a partial order reduction, which is very beneficial, but you get this kind of partial order reduction very often. So there are techniques for this, basically removing all these redundant schedules, and this is what we use, and then it gets used in any kind of path exploration tool, including the tools for model checking actors and so on. So I guess I won't have time to get through describing this technique, but the idea is basically to avoid the shuffle of these two things. So, and this is done with enabled sets and so on. So I think we are probably, yeah.
But I think you need a more powerful technique here than just partial order reduction, because the repetition of messages does count here, right?
Right.
Initially unbounded buffers.
Yes. So yeah. So we do have. So I mean, for purposes of testing, you often have a closed system assumption, and then you know how many sort of messages are in there, and you shuffle them. Now, if you've got an open system, then you need some kind of abstraction, exactly, right? And so, yeah, so we have techniques for that. Let's see. So, yeah, so there is one technique here in terms of what's enabled, and oops, I don't want the clipboard. Yeah, so let's just anyway. So this particular technique gives you lots of speed up in these examples, anywhere from just twice the speed up to 40 times the speed up. So I will stop at this point, give you some view of things. I think we are out of time, so leave time for questions. Yeah.
Thank you very much.
Yes, so you mentioned this location transparency as one of the
right.
assumptions and the benefits
yeah.
of the model. But at the same time, I've been reading about resource-aware concurrent programming, and also there's criticism of remote method calls with remote objects.
Right.
So what's the...
Well, so yeah, so...
Can you repeat the question?
So the question is that this location transparency. I've sort of argued for location transparency. On the other hand, if remote calls, for example, are expensive, now I'm sort of elaborating on the question, and so shouldn't the programmer be aware that it's a remote call? There are again things like fault tolerance issues. Fault tolerance may vary whether it's remote or local, and so on. So here we sort of get into the question of two kinds of things. One is, what is the right level of abstraction, right? So now imagine that your machines had some bounded memory, less of a problem these days, and you wrote a program to compute the stack. But you said, no, don't ever write a recursive program because you don't know what the stack bound is. The only thing you can do is explicitly allocate this memory, right? And of course, things then become very hairy. And programmers used to do this in assembly language. Right? Similarly, now you go to a multi-core architecture, you get 100 cores or 50 cores, and they're using a message passing thing. There'll be very different costs associated, very different parameters than if you're in the cloud or if you're in a different context. If I've written a program, should I be forced to rewrite that program? Every time things change, the amount of memory might be going down because multi-core, you're getting distributed memory, you're stacking the memory onto the processing elements, and so on. So you've got sort of a variety of architectures, and in some sense, what you're trying to do and what concurrency it has, if you stop trying to optimize, and it's kind of almost like the functional programming bias in the sequential world, if you stop trying to optimize at the time that you're expressing it, then your reasoning and your bugs and so on will be simpler. So then comes the second half of the question, well, what about the efficiency? And which was my motivation for showing you that, yes, there are efficiency issues, and yes, there are ways of dealing with them. So you've got sort of this continuation kind of transform. You can take threads and do tricks with the threads. You can figure out when you just can send the thing by reference. So one part of the answer would be, well, how much can the system figure out? For example, load balancing and locality and optimize. Now let's assume for a moment that the system is not able to do that good a job. Then I would say at a minimum what the language should do is provide a separation of design concerns. So you've got this program, it's perfectly recursive, and now it gives you a tool that estimates the memory use. That would be the analogy. So you've got this program and it's perfectly location transparent. It has been written abstractly. And now you've got these pieces, and the tool comes back and asks you, I cannot figure out should these go on the same node or not. And maybe you give some hints to the compiler. So I would say that a separation of design concerns of things that you can then throw away or rewrite without touching the logic of the thing, logic of the program would be the way to go. At least that's the way we should think about it as programming language people. Right? Yeah.
Sorry. Okay. I get the feeling that you have tried to get as simple as possible definition of distributed computing with this fairness property, which gives very weak requirements.
Right.
And you also show that it creates some problems with different scheduling orders. So it feels like it's not complete. It's like lacking something that you have to add afterwards. You have tried many different approaches.
Right, so people are experimenting with lots of approaches, and there is basically the interesting part of concurrency ought to be this problem of coordination. And in fact, a couple of my students did an empirical study with Ralph Johnson, who's a very practical-oriented software engineering guy at Illinois, on how people were using actors in open source. So many of the systems I mentioned, of course, there's some company behind it, and it's proprietary software, you can't get at it, and so on. But in open source projects where people had sort of agreed, okay, we're going to use actors, and they're sort of volunteering and checking things in, and then you check this. And very often they observe that there are places where people just break the abstraction and throw in a shared variable. And they asked the programmer, and they thought, well, maybe the programmer didn't understand the model or something, and no, it was just they wish they could have done it the active way, but it just seemed like the simplest thing to do. And when they looked at these examples, it seemed most of the time they were doing this for synchronization. Make it very easy by throwing in one variable to coordinate things. So people are sort of struggling. Now the problem with that is, of course, that makes it harder to reason. So what we want to do, the reason we've been experimenting with this notion of constraints, and the constraints are in terms of the interface rather than in terms of the representation. So by saying what orders of messages are legal, you're essentially constraining the atomicity property instead of, for example, taking the messages and implementing a two-phase commit on the messages in the representation of the object.
Is that what you call protocol?
Yeah, exactly. So what we are thinking of the protocol as is a meta-programming problem. So you have, for example, a behavior which is a well-defined method which moves, for example, this pen. This robot moves this pen hand to this point. And now this thing grasps and moves it away. Now you've got these two things concurrent, and now if you program them independently, there's a good chance it falls to the ground. So now I give a constraint that says this must grab it before this one releases it. Right? So if you now think of these things as messages, there's a release message, there's a grasp message. I've ordered these messages in independent actors. If I put this into the code of the communication of these actors, then I go to a different context. I have to then add to the code. I need to move this chair. I need them to do it atomically. Then I need a two-phase commit. Moreover, I can never reuse that code for the two-phase commit. So what I instead would recommend is we think of these things as constraints, and what these constraints affect is the scheduling. Rather than, so they affect when things are done, in this coordination case, and the when should be expressed in terms of the what and not in terms of the how. And by doing this, you can reuse the protocols in different contexts by basically parameterizing them. In fact, we have a protocol language with which we've done that, and it should be really a meta-programming problem. Otherwise, the programs become too complicated.
Also, about testing
Yeah.
in this framework, what do you think is the main challenge that is not yet addressed, for example, with partial order reduction or the existing techniques?
Yeah, so I mean, there isn't, for example, any tool with a good integration of static analysis and partial order reduction. So even if the order matters from the outside, if it's not affecting the state, for example, then so there's not a good integration of the two things. So that's an example where there is still.
What about choosing, for example, data parameters? Since you encapsulate the state in the actor,
right.
You're not supposed to look into the, say, actual working of actor. But
yeah.
Then for testing, you need to partition data domain, right?
Right. So then you need some compositional testing tools, and we're still weak in those. And also, if you've got a meta language, then testing the meta language, what constraints is it exporting, and is it interfering, and you know, causing deadlocks or other things. So
and that's something that has not yet.
No, has not been done either. Yeah.
Zach? How do you relate the mobility concepts in actors versus mobility concepts in pi calculus?
So the pi calculus was inspired by actors. In fact, I had discussions with Robin Milner back in '80s when he visited MIT and the CCS, and he thought actors were too fluid to capture. And in fact, he had a huge following in Europe, and every time I'd be at some conference, they'd say, no, 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 actors, they're too fluid. And then it was interesting when Milner finally did the pi calculus, all of those guys who were telling me that this couldn't be done, that there could be no formal framework, they all start doing pi calculus. So and there's sort of some kind of priesthood there that the sect followed Milner. But if you read the Turing Award lecture, you sort of get this. Now, the relation between actors and the pi calculus, in fact, is quite complicated. We've analyzed it in detail. So you might, at the superficial level, say, okay, the pi calculus has synchronous communication and actors have asynchronous communication. But in fact, if you look at the pi calculus, since you have the ability to create processes, as they call it there, and those processes are asynchronous, basically what this means is you can create a message as a process which does nothing once it's delivered, and now you get asynchronous pi. Pi calculus has other issues. In actors, we have unique names. Each actor has a unique name. In the pi calculus, you could have two things pop up with the same name, and you get this sort of funny non-determinism from independent processes. So it's not really a programming language or a programming framework. In the pi calculus, you can receive a name and turn around and listen on that name. So this is the equivalent of I send you, you give me your address so that I can send you a message, or give me somebody else's address so I can send them a message. And what I do is turn around and steal his mail, non-deterministically, of course. He gets some, I get some. So you have sort of lack of this ontological commitment to any notion of this kind of encapsulation, or there's kind of a fluidity there. Now, of course, it's nice and algebraic and simple in some ways, but you can put axioms, essentially what would be called a type system, on the pi calculus to regain the discipline of the actor model. And when people try to implement the pi calculus, a good example was this PIC language. It's in fact an actor language with asynchronous messages and fairness, which is again something not primitive in the pi calculus model, uniqueness of the names, because otherwise the programmer would go quite nuts trying to deal with it. So then the question becomes, is it a good tool for reasoning? Because there's such a gap. It's like, do you want to reason, for example, in the lambda calculus, or do you want to reason in terms of the more abstract or something more disciplined than the fluidity? But it does, the motivation of the move from CCS to pi was to capture actors, and in some ways it does that.
Yes, so, okay, so let's say that I have a highly parallel computational substrate, and I want to use the actor model to distribute my computations on it. I need some sort of cost model for the communication to determine how granular this should be.
Right.
What do I need to know about, the hardware, as it were, in order to get enough information into the cost model?
Yeah, so this actually gets very complicated, and we've done a little bit of work on this. And if you look at some, so I got interested in the quicksort example because it's a canonical example for the functional and the logic programming guys. And I looked at that and I said, wait a minute, log n speed up. I give you 1 million processors for 1 million numbers in theory, and you're going to speed it up by 20. So can we do better? And in fact, I developed a quicksort algorithm that with some more theoretically minded people who were, or less lazy people, I should say, were willing to do all the details of the algorithm and show that the properties that I had asserted were actually correct. So then it gets complicated because there's sort of data being sent, and you have message costs. It's even more complicated because the question of whether you can overlap computation and communication. So there are models of parallelism, such as bulk synchronous processing, which say, okay, or basically everybody gets to some point, then they resynchronize, and then you restart. It's a systolic kind of thing. But the scalability of algorithms is very different if you're able to mask communication costs. So if you do a context, you send a message, and now you have to wait for some value, but something else does a computation in the interim, right? So you sort of go on. And so now the cost of the communication is just the cost of sort of starting the pipeline, rather than waiting for the round trip and then waiting for the next step and so on. So we have developed some models. There are some papers. The models aren't as formalized as we'd like them to be. But Vipin Kumar at Minnesota did quite a bit of work on scalability and much of that is quite applicable.
If I understood correctly, that if you have a sender and receiver with
Right.
the property that every send and receive messages have this diamond property, which you just showed, then the system will be correct, because whatever order you take and whatever order you do.
No, well, not that the system will be correct, but that when you reason about the system, you don't have to worry about the other orders. But you don't always have the diamond property.
Yeah, so what you do if you don't have a diamond?
In fact, most of the time you won't have the diamond property.
Yeah.
Things that have diamond properties are very boring. They're only interesting to mathematicians.
Okay.
If you're playing games,
Yeah.
you don't want the diamond properties. Somebody's going to win.
Yeah.
If you've got a bank account, it matters whether you make a deposit first or the withdrawal first. You don't have a diamond property, right? If you have an airline reservation, you definitely don't want a diamond property.
So how do you ensure if you don't have a diamond, then what's the way to go?
Well, but that's exactly the specification of the problem. If you have an airline seat, then the order in which they're booked reserves that seat, and the world changes. So messages have consequences, to paraphrase.
But there are some practical constraints on the, say, relative order of these processes, right? So you don't want the one process to go, say, 10,000 steps and the other one stay resolute without any move, and then say this is a bug, this is something that doesn't happen, right? I mean, what I'm saying is that it is true that diamond property doesn't hold, but there are certain types of concurrency that you should prune because they are not realistic.
Yes, so that gets into sort of more probabilistic analysis. And in fact, there's even trade-offs with efficiency. So for example, you know, if I've got message sending, so one of the things we do if we're compiling, the message send is just, if it's local, it's transformed into a function call, so you don't have a thread, you don't have to allocate resources, you just basically use the stack and proceed. Now, of course, if this sequence of calls keeps going, you could have an infinite loop, and then you're starving everybody else, and you lose fairness. So what you're going to do is to say, okay, time out after some point, and turn this message send, instead of this function call, turn it back into a message send, and give something else a chance to go. Right? Now, of course, when you should do this is an optimization question. So the more often you sort of time out, you're going to pay the price of sending a message. But if you take 1,000 steps before you turn it into a message, then your cost, and you know, if it takes 1,000th of the time, then your cost is 50%. Now you make it 10,000, your cost is 5%, so on. So there's sort of this sort of practical trade-off. And then you're right, at some point the probability becomes very small. So one of the things that we've played around with reasoning is building some kind of probabilistic model to say that, you know, indefinite postponement is not a likely scenario in the larger system. So.
All right. So on this note, I would like to suggest that we continue the discussions with the coffee and cake that are now waiting outside for us. There's a tradition of giving the speaker a small present
Oh,
here at
thank
the university.
you.
So thank you very much for this wonderful talk.
Thank you.